All right, hello again, 102 students. Got a question here on number 18. Let's run through this one. This one, there's actually quite a few directions we can go with it. But there's a couple of big things here. One of the first ones right here is it says Mars has a radius that is about 0.53 the Earth's radius. Okay, and it has a mass of only about 0.11. I'll call it 11% of the Earth's mass. Estimate the acceleration due to gravity on Mars. Now, notice it didn't say the force; it said the acceleration. So we need to put this chapter and the past chapter, or actually the chapter before that, I think 3, together, because here is this chapter. This says, okay, the universal law of gravity says simply this, that the force between any two objects would be calculated in this way. So if you were asking, how much would you weigh on Mars? You would need to know something like this. You would need to know the two objects. One would be your mass, and the other one would be the mass of the planet you're on, which is Mars. You would then need to divide that by the distance between them. And if you're standing on the surface of Mars, then that would be the radius of Mars, just like we do for the Earth. If you want to know your weight on the Earth, you would put in the mass of the Earth, the mass of you, and then the radius, because that's the distance between you and the center of the Earth. But let me not get bogged down with the Earth. Let me just stay focused on Mars. So I would need the mass of Mars, the mass of me, and then the radius or the distance between them, which, like, again, if I'm on the surface. Now, this is the force, but they didn't ask for force. This one asked for acceleration. So let me take you back 2 chapters and point out that acceleration is force divided by mass. Now, when I put a mass down here, it begs the question. Now, if I'm trying to find the acceleration on Mars, so maybe I'd say, here's Mars. I guess I would need to know my force when I'm on Mars, and I would be dividing it by what? Because up here, the force has 2 masses. One is Mars, and the other is the object, say you. So, let's say you were to jump off a rock. And what's your acceleration? And the answer to that down here, going back to chapter 3, is this is the mass of, the object that is being accelerated. So this would be, would be me. Here's why I say that, because if I go to try to figure out what is the acceleration on Mars, and for force, I put in this universal law of gravitation. I would have G, I'd have M1, I'd have M2, and I would divide by R squared. And when I divide by M, it brings up the question, which M is it? Is it the mass of the Mars itself? So let me call that number 1. Let me just put mass of M for Mars. Or is it mass of the object that's going to be accelerating? Maybe maybe it's me jumping off a rock. Maybe it's me dropping a baseball. I'll just call it an object. But as I said, this would actually be the object. So that's important to know which one cancels off, because then you're going to be left with a G, and there's only going to be one mass in the numerator after that. And you got to remember, which one is it? And so in this case, it would be the mass of the Mars. Or if it was, planet Earth, this would be the mass of planet Earth. Basically, the object cancels off, and so you're left with the mass of that particular object. So this is kind of a little recipe. I suppose you could even, just call it a formula and say, look, this is a formula we learned in the book. And then if you go to calculate the acceleration. But I wanted to point out that it's really not something worth memorizing. If you're learning the universal law of gravity and you've already learned Newton's second law, put the 2 together, and that's what you get. So if this problem had asked for the acceleration on Jupiter, I guess I would put the mass of Jupiter and then the radius of Jupiter. All right. So that's kind of the big step, is to say, look, they're not asking for force, but their acceleration. So that's why I only have 1 mass here. Now, the other thing about this, then, is they kind of give a hint towards what is the radius of Mars, because they say it's 53% of the radius of the Earth, and the mass of Mars, which they say is about 11% of the mass of the Earth. Because really at this point, I could just, look this up. I could look up, hey, what is the mass of Mars and what is the radius of Mars, and punch them in and be done, and not even use the numbers that are given there. And I wouldn't say that that's wrong, but I don't think that's the way the author wants us to go, given that they've given us some basic information. So let me do this. Let me continue this problem by doing this. Right here where it says the mass of Mars, let me put 11% of the mass of the Earth. Okay. And that's kind of the step. And then the same thing with the radius. They say the radius is 53% of the radius, and let me just put an E here, of the Earth. Now, if we simplify this math a little bit, we can put the 11% out in front. We could even put the 53% squared out in front. And we would be left with a g times the mass of the Earth over the radius of the Earth squared. Okay. And so, like I said earlier, we could have just gone back here and looked up the mass of the Earth, Mars, and the radius of Mars, and be done with it. Now, we've changed it into something a little different, where we are going to have to look up the mass of the Earth and the radius of the Earth. And then whatever we get, we would then multiply by that number. And I wouldn't say that's much of an advantage, but I'm going to take it even one more step that I'm hoping some of you see this coming. I don't even need to look these up. I say that because if you just focus on this right here, ignore the numbers out in front, just that, and you go back to what we said back here about acceleration, would just have the capital G and one of the masses and the radius of that planet. This right here is the acceleration on that planet. This number right here would be the acceleration of an object on Earth. And then when you multiply by these numbers out in front, you would get the acceleration on Mars. But ignoring these numbers out in front, this is the acceleration on Earth. So I'm not even going to bother to look up the mass of the Earth or the radius of the Earth. I just know that the acceleration of something on Earth is 9.8, or if you want to just kind of round it to 10, that's fine. But I think that's what the author really wanted you to do, not really look these up. Because if that was the case, he probably would have just left it alone and said, look, go ahead and look up the mass of Mars and the radius of Mars. And there's not much of a difference between these two steps. But I think a big thing he wanted you to do is make this connection that, hey, we can now do a comparison to any other planet. We would just have some prefactor multiplied by the 9.8 if we know things like the mass and the radius as a percentage of the Earth. So that's kind of a little cleverness that can easily get passed by. So if you just look these up, that's fine. That's a good step. But I think this is even better. And so I wanted to kind of get you to see a comparison of numbers. Now, I didn't have to actually look anything up because I already knew the 9.8. And so let me calculate this out. The numerator is 0.11 times 9.8, and then the denominator is 0.53 squared. And this gives me an acceleration of about 3.84 meters per second squared. And that was the cleverness of this problem. All right, enjoy.